This recording is to help you with lesson 9.03 on geometric sequences. Now, we are talking about arithmetic sequences where we added or subtracted a number to get to the next term in the sequence. Now with geometric, we are going to multiply. And we can multiply by an integer or we can multiply by a fraction. Because remember, multiplying by a fraction is the same thing as dividing. So that's why we can multiply or divide to get to our next number. So let's start here. We have to determine whether our sequence is geometric. So previously with the arithmetic one is we would add or subtract. Now let's see if we can divide to see if the ratio is the same each time. So let's start with the second term and divide by the first. So if I take the second term and divide by the first, I get -1/2. Now every time I do this, my ratio should be -1/2 for it to be geometric. So let's take the third term and divide by the second. So the third term divide by the second. I do have to change this to a multiplication problem. Reducing, I get a -1/2. And I can keep going and testing if I want to. But I do notice that, in fact, it is geometric, and my ratio is going to be the -1/2. All right, for the next one, we're going to find the first 5 terms of a geometric sequence. That just means we take the first term and we multiply by that ratio. So the first term is 5, and the ratio is -1/10. Let's multiply those. 5 times -1/10 is -1/2. So here's the first term. Second term is -1/2. So we take that -1/2 and we multiply by the ratio. And simplifying that gives us a +120. Now we're going to take that answer and multiply by the ratio. Simplifying that gives me a -1/200. And we take that and multiply by the ratio. And you can see our numbers are going to get pretty small here pretty quickly. And we get a +1/2000. And we can keep going like that, but they only ask for the first 5 terms, so we can stop there. Okay, so the next one we need to find the nth term of the geometric sequence, and here they're telling us that n is 3. So we need to find the third term. A couple ways we can go about this. If we know the first term and we know the ratio, we could just multiply that 3 times until we get the third term. But we don't actually know the ratio. I know my first term is 16, and the fourth term is 27/4. So what I'm going to do is I'm going to work backwards to try and find that ratio. Okay? So we have this formula of the nth term right here. How I can find the nth term. Well, let's use the information of the last term we're given, or the fourth term. So the fourth term is 27/4. I know the first term is 16, and n is 4, because right here is your n, right? So 4 minus 1 is 3. We're going to work backwards to try to solve for r. So I'm going to start by dividing both sides by 16. After that, I get 24/64 equals r cubed. I'm going to take the cubed root of each. And I'll get 3/4, because 3 times 3 times 3 is 27. And 4 times 4 times 4 is 64. So now I have my r. I have all the information I need to find the third term. Okay, because if I look at my equation here, I know the first term is 16. I now know r is 3/4. And n is 3, because I want to find that third term. So 3 minus 1 is 2. So all that's left for us to do is simplify this. So 3 squared is 9, 4 squared is 16. 16 times 9/16 is just 9. So the third term of that geometric sequence is 9. The next one is just a graphing question. We notice that r is greater than 1. So I know that my graph is going to be increasing, so going upwards. Okay? All geometric sequences have that, that type of graph where it'll increase or decrease quite rapidly there because you're multiplying by that same ratio each time. Okay? So we just need to kind of see which graph that's increasing will match my equation given. So you can test a couple of your values for plugging 1, 2, 3, 4, 5 in for n and seeing what your outcome is. When I plug 1 in, I do get the outcome of 18, so the point 118 will be on your graph there. It turns out that this will match graph B. Okay, next I want to find the sum. So the sum of a geometric sequence can be found with this formula right here. So I need to know the first term, I need to know what r is, and I need to know how many terms I'm actually dealing with for n. So let's find the first term, because I want to eventually start plugging stuff into my formula. So my first term, when I plug 0, because look at n starts with 0 in this one. Okay, anything to the 0 power is 1, so 3 times 1 is 3. So the first term in this sequence is 3. R, remember, is whatever is in parentheses there, so the 3/2. And n is the number of terms. So between 0 and 20, there are 21 terms. And that's a little bit different because usually we're used to working with 1 to some number. Okay, this time it is from 0. Notice that change. It's a little bit different than what we were used to working with in the past. So I have to tack on that extra term there. Okay, and now I'm going to divide by 1 minus r. From this point, I would use my calculator to try and simplify it. It does make sense, or does matter, the order that you do things in. So make sure you have a lot of extra parentheses involved here. I'm going to see if I can maybe write it with the correct number of parentheses. And then we'll have, I'm going to come down here to continue. So this is how we should type it into our calculator. I believe I have all the parentheses needed there. When we type that into our calculator, then we should get an answer of 29,921.31. And the last one is actually writing a summation notation. Remember, for summation notation, we need the sigma. We need a starting and an ending point and a formula. Okay, the formula we use for geometric is represented by that nth term. Okay, so we have this generic formula here. Let's plug in the information. I know my first term is 5. I know that r. So looking at this, I can easily find r. It looks like r is 3. 5 times 3 is 15. 15 times 3 is 45. And then I keep my n minus 1. Okay. I'm starting with 1. What am I finishing with? How do I get 7? How do I know that there are 7 terms in this sum here? Well, I know the last one is 365. So let's turn to this formula that we came up with, or the equation, and set it equal to 365 and try to solve for n, so we can find that stopping point. Well, the first thing I would do is I would divide each side by 5. And when I divide each side by 5, I get this right here. Now, there's a couple things we can do. We can try to take the natural log of both sides and then bring that n minus 1 out front. Or we can try to rewrite 729 so that it's 3 to some power. Whatever you prefer, you'll get the same answer in the end either way. I chose to write 729 as 3 to the 6th power. If the bases are the same, remember you can set your exponents equal to each other. And they have the same base of 3, so that's why I did 6 equals n minus 1. Okay? I added 1 to both sides to get n equals 7. And I needed to know that n equaled 7 because that was where I stop. Okay? So this actually has 6 terms in it, or 7 terms. Okay? And we start with n equaling 1 and end with n equaling 7. So here is the proper sigma notation, or summation notation there, for this geometric sequence.